Lab 4 Rope Physics Spring Mass Lab by Central Park Tech. Our objective is to build a computational model that allows us to predict the motion of our mass oscillating on our spring. We want to compare the predicted motion of the mass and the observed motion in the animation we get from the code. Our procedure is the following. We constructed the computational model using information from Rope Physics 1 and Rope Physics 2 videos in Coursera. We graphed the data from the motion of the observed data and compare it to the animation extracted from our code, predicting the motion of the mass oscillating on our spring. The initial conditions were the following. The mass was 0.402 kilograms, the start time was 0 seconds, the position vector was had an x component of negative 0.118, a y component of negative 0.651, and a z component of 0. The relaxed length of the spring was 0.26 meters, and the time per oscillation was 1.33 seconds. And our spring constant, K, was 8.97 newtons per meter. The physics principles we are going to need to know is Newton's second law, which says an acceleration of an object is dependent upon two variables. One, the force acting upon the object, and two, the mass of the object. The acceleration of the object depends directly upon the net force acting upon the object, and inversely upon the mass of the object. The second principle we are going to need to know is the energy principle, which says the change in kinetic energy of an object equals the net force done on the object, and the total net forces in the entire system equals 0. All energy within the system stays there as well. Now, for our model predictions, our first one is just our model we predicted. Just our first model prediction is here, the following, which is the model we use from our initial information we got from Tracker. And as you can see, our model here begins to go counterclockwise and then stops and starts to go clockwise kind of while it's oscillating on the spring. Whereas in Tracker, our mass just goes counterclockwise the entire time. So that's a little different. It could be due to the fact that we did something wrong initially while we were plugging in our data, or it's just the way everything was predicted from our code. Now, our model predictions versus our actual data. For that, we actually made another code for both, so you can see the motion of both. And as you just saw in Tracker, our object, which is actually represented here by the red ball from the mass in Tracker, continues to go counterclockwise, while the blue ball, which is our predicted motion of the object, tends to stop and then start to go the other way. Our energy graphs are very important as well, and we can see our energy graph here when we run our module. And the yellow means the total energy in the system, which we know from our energy principle equals 0. So that makes sense why that is 0. The red is the initial, is the potential energy of the spring, which makes sense as well if we see it in Tracker, because the spring is spinning round and round. The spring goes up and down and oscillates back and forth, so you wouldn't expect it to be constant. And the green is the gravity. Sorry, the green is the change in gravity, is the change in gravitational potential energy, which makes sense as well because that changes from kinetic to potential, so it goes up and down the whole time when our mass is going round and round. And the red is the potential energy of the spring, which changes back and forth from kinetic to potential, so you can understand why that changes so much and is really has like high frequency on the graph. And then the blue is the change in the kinetic energy, which makes sense, just like the potential energy, because it kind of bounces back and forth because it changes back and forth between the different types of energies. We want to know what this means for our model system. Is the energy principle satisfied? Well, we know that from the energy principle, like we can go back to the energy principle and look, we know from the energy principle that the change in kinetic energy of an object equals the net force done on the object. So we don't necessarily see that here, but we do see how the total net force in the object does equal 0. So it does satisfy it in that case. And then our second question is, using the data we obtained in Tracker, we need to make two separate estimates of oscillation periods. First, by estimating the period of oscillation from the x position data, which we did, and we found it was 0.179. And the second, by estimating the period of oscillation from the y position data, which we also found was 0.985. And we want to compare the two estimates. Well, we found the oscillation period initially to be 1.33. So these new oscillation periods could be different due to the fact how much it moves, how much our object is moving. But it does make sense that those numbers are close to the total oscillation period because the object in the x and y plane do move quite a bit. Thank you very much for watching.